Alrighty, so we're gonna move on to 3.5 today, which is talking about zeros of polynomial functions. So the learning target is going to be I can identify the zeros of polynomials. And what that means when we're saying zeros is just like it was with quadratics, when we did quadratic equations, zeros refers to same thing as, I'm going to list all the kind of synonyms here. Zeros are also called x-intercepts, sometimes called solutions, sometimes called roots. All those words mean the same thing. So those are all synonyms for one another. And so you'll see those kind of used interchangeably throughout various equations and problems and this and that. So we're going to use that zero product property from chapter 2. So it says, what are the zeros of this function? Now this one is already in factored form. And when it's in factored form like this, where you have all these different linear factors, it's really easy to identify the zeros because you got to say what number will make each of these parts be zero. So this right here is going to just be zero, because if this is a zero and you multiply it times anything, you're going to get zero. This one is going to be 4, because 4 minus 4 gives you 0 here. And this one's going to be -3, because -3 plus 3 makes it be a 0. So those are going to be our zeros or our solutions. We'd say x equals 0, 4, or -3. That's be our answer to the problem. Now it also says to graph this function. So what that means is that this function is going to cross the x-axis at these 3 spots. So if we were going to graph this, and we'll put it in the calculator in a second, but I just want to show you like what you would know going into it. You know it has to cross at 0, it has to cross at 4, and it has to cross at -3. Now what we don't know is if it starts down here and maybe it loops like so, or maybe it starts up here, maybe it loops like so. We don't know that yet. We can figure it out based off of end behavior. So if we look back, boom, just like that. If we look back and remember back in 3.1, we did things with like odd and even degrees, and positive and leading coefficients. We were able to tell whether it was going to go, down and up or up and up and those types of things. We could use that here to figure this out. So let's take a look. All right, so in my case, this isn't all distributed out, but if it was, we'd have x times x times x, and this lead term would be an x cubed. And there'd be a lot of other stuff, but we don't really care about that stuff. But basically, this is going to be odd and positive. So that means it's going to be a down to up. So I can actually sketch this graph, and I can have like a pretty good feel as to what's going to happen without a calculator at all. Now, obviously, you do have one, and you could graph it, and you can see the same kind of thing. So I'm going to do that too. And this might be the route you go, but it's kind of good to have just sort of a big picture idea of what's going on here. So if we did just graph this, we're going to see something pretty similar. And we're going to see it crosses at -3, 0, and 4. Now, again, we don't know how high or low it goes when I was making my sketch. So when we do it here, we can see, okay, it goes past 10 and past -10. But either way, we can see basically the same concept. All right, so here's the big idea today, is if you can get something into factored form, the zeros are really easy to identify using that zero product property. So right here it says, factor the function, and then use the zeros to sketch the graph. All right, so what do we have here? We can pull a 4x out of everything as a GCF. That's going to leave us with x squared plus x minus 6. And then we need to factor this. So factors of -6 that are going to add to 1 are going to be 3 and -2. So this is going to factor x plus 3, x minus 2. And now that it's in factored form, we can identify our solutions. So 0 would be at 0, -3, +2. And that would be our answers to that problem. Also says sketch the graph. So once again, 0, -3, and 2. So 0, -3, and 2. And this is a third degree, and it's positive, so it's going to go down to up. So it's going to start down here, and it's going to loop through and turn at each of those spots. So it's going to have to look a little something like that. Okay, very similar to the previous one. Once again, you can graph it in the calc or Desmos, whatever, and you can check and see it that way too. Next one here, it wants us to factor this out. Ooh, this is a little trickier. So this one, x to the 4th, this is a difference of squares. This is x squared times x squared. This is 9 times 9. So if we go x squared plus 9, x squared minus 9. That's going to work. And then those are also a sum and a difference of squares. So this one's just another difference of squares. This is going to be x plus 3 and x minus 3. This is a sum of squares. So it's going to be x plus 3i and x minus 3i. So all our factoring from previous days is it's back again. It doesn't go away. So this has 3 solutions. Or sorry, this has 4 solutions. 2 of them are imaginary. So it's negative 3i and positive 3i. And 2 of them are real, negative 3 and positive 3. And this graph then has 4 actual solutions, but only 2 real solutions. So when you go to graph this, it's going to cross at negative 3 and 3. And then imaginary solutions can't get graphed. So just for the sake of things here, let's graph this so you can see what it would look like in the calculator. We can talk about why it looks the way it looks. So if I put it in here and I graph it, I see this. And the reason I see this is I'm zoomed in pretty far. So if I zoom out, because it's going to cross down here at 81. So let's go ahead and just make it go down to 81. Let's go to negative 100. Let's keep these at 10s. Sorry about that. And so now we can see the graph does just look like that. You know, it's way down here at negative 81, and the graph's going to be coming up through here and through here. So like we've seen before, only real solutions show up on the graph. Imaginaries will not. Cool. All right, so let's look at example 2 now. So example 2 talks about how you can have what we call, a multiple zero. So that's when a 0 appears more than once on the graph. This graph, this problem right here, has just 2 singular zeros. It has a 0 at 1 and a 0 at negative 2. Boom, boom. This one has, because this is squared, means that this 0 that appears at 1 actually appears twice. We would say it has a multiplicity of 2. And this one just appears once. Now, what happens with this is, even though these problems have the same exact 2 zeros, you know, negative 2 and 1, negative 2 and 1, they look very different. And they look different because of this multiplicity concept. The fact that this 0 appears twice means that it's not going to cross through. It means that when it hits that spot, it's going to bounce up. And the rule that we're going to learn as we look at a couple of these, so let's just kind of look at these other 2 as well. You'll notice these are all basically the same problem. Now this one's to the 3rd power. So now this is 1 with multiplicity 3 and negative 2. And this one crosses through. These 2 are kind of similar. And then this one is 1 with a multiplicity of 4. It appears 4 times. And this one is kind of similar to this one, where it touches it and turns. And so the takeaway here is exactly the 2 sentences that it says right down here. It says if the multiplicity is odd, meaning it's to the 1st, 3rd, 5th, 7th power, whatever, then it's going to cross through. So all odd multiplicities will cross through at that number. Now they might do a little wiggle like this, but they are going to go all the way through. And anytime it's even, it's going to touch that point and turn. So it's going to be what they say is a turning point at the x-axis. So that's for a 2, a 4, a 6, an 8, so on. Anytime it goes there, instead of crossing through and heading downward, it hits it and turns back up. Hits it and turns back up. So this is this concept of what's called multiplicity. So for right now, let's just look at identifying this and make sure it kind of makes sense as far as what we're doing. So it says, describe the behavior of the graph of the function at each of its zeros. So this graph has zeros at 0, negative 4, and 1, right? Because those are the numbers that would make each of these parts equal 0. These 2 are both to the 1st power. So these both have multiplicity 1. This has multiplicity 1. This one's to the 4th power, so therefore it has multiplicity, 4. I just write mult for multiplicity. But multiplicity is saying how many times that 0 appears. So 1 time, 4 times. And then it says, what is the behavior? Again, the rules are if it's odd, it's going to cross. So both of these are going to cross. This one is even, so it's going to be a turning point. So we're going to say turning point. If I take a second and graph this, you're going to see that this graph is going to do just that. So let me type it in for us. And might have to go back to the standard window. Ooh, actually, let's get the job done. So let's zoom it in. Sorry, I want to see a little bit closer there. So we can see it definitely crosses at -4. It crosses at 0. And then it does appear to have a turning point. I think if we zoom in a little further, we can see that a little better as far as exactly what's happening at 1 there. Yeah, there we go. Perfect. So now you can see it does cross through at 0, like we said. But then at 1, it turns. So this is doing what we said. You just got to kind of zoom around and see that it's doing those things. But the multiplicity does give you that information. So we can do the same exact thing with this one. This one's going to have imaginary zeros, same as the other one we had. So it's going to have like, plus or minus 3i. It's the same exact factor we saw earlier. So that one's not going to show up on the graph at all. It does have multiplicity 1, but like, again, not on the graph, so we really don't have to worry about that one. This is going to be 1 with multiplicity 5. And this is going to be -2 with multiplicity 2. So according to this graph should cross at 1, and it should turn at -2. So let's go ahead and throw it in there and take a look at it. All right, so this first part isn't going to show up on the graph. It's just going to move some stuff around, but you're not going to see any zeros from it. But from these ones, the x minus 1, oops, one too many parentheses there, to the 5th, and x plus 2 to the 2nd. Okay. And we're all zoomed in, so let's get out of here. Yeah, it kind of shows what we want to see, but let's zoom out. Okay. So at 1, our graph is definitely crossing. And at -2, I am not seeing what I want to see there. Hold on. Okay, so I did find it on here. This is one of these that decimal is going to show it a whole lot clearer than this. But the -2, I had to like zoom in really far. So here's -2. The graph just spikes very, very quickly. So it touches and turns. So it is doing what we said there. But again, this one, not a great calculator example, but it does show what we're looking for there. So again, the big takeaways today are being able to identify zeros from when you get it into factored form. And if zeros appear more than once, they can cause what we call multiplicity, where even ones have turning points and odd multiplicities have where it just crosses through.